are watching video number 2 on probability. Hopefully by now you've watched video number 1 on Introduction to Probability. You have completed the classwork on Introduction and also the homework. So we are leading up to some more investigations with different types of probability, and again, remember that you are free to use your calculator on this. So we're starting off with 2 situations here. Situation number 1, 2 cards are selected in sequence from a deck of cards. Find the probability the second card is a 2, given that the first card is a king. Scenario 2, we toss a fair coin twice. Find the probability that the second is tails, given that the first is also tails. How are the 2 scenarios the same? Well, in both scenarios, you have 2 events happening in a row. But how are they different? One is dependent on the first event. The first situation says that you're selecting 2 cards in a sequence. You're finding the probability the second card is a 2, given the first card is a king. How many cards are in your deck if you know the first card is a king? You no longer have 52 cards to pick from, you just have 51. And so, given the first event has already happened, it changes the probability of that second event. Whereas, tossing a fair coin twice, that's an independent event. The fact that the first toss was tails makes no influence on the second toss being tails. The probability that second is tails is still 1/2. So that's what we're taking a look at today. And so this is called conditional probability. So conditional probability is the probability of an event occurring given that one event has already occurred. That conditional probability can be independent, as we see above. It can also be dependent, as we see above. You denote conditional probability with the notation you see over here. The probability of B, this vertical line means given A. So if I were to go back to our 2 examples and use that notation, in the first example it would be the probability of two given king. And in the second, it would be the probability of tails given tails. So let me go back to the first one for just a second. What's the probability we draw a 2 given the first card was a king? So that's our notation there. So next we see that we have a table, and this table involves the distribution of goals for boys and girls at Dobyns-Bennett High School. So first, it says find the probability that you randomly select someone that plays sports given they're a girl. So what do you know to be true about this person? You already know the person you select is a girl. So that changes the denominator to 251. Out of the girls, how many have goals related to sports? That would be 30 over 251. And of course, you can type that in your calculator if you so choose to. Next, it says find the probability that the person has goals with grades given it's a boy. What do you know to be true about this person? You know they are a boy, and so you know you're only looking out of the 227 boys. And out of those boys, how many have goals about grades? That would be 117. And so type that in your calculator and you can get a decimal. And the last one here says, find the probability that the person is a girl given they commented on their goal being popular. So this time, what do we know to be true about this person? We know that their goal is popularity. So our denominator is out of the 141 students who responded about popularity being their goal. And out of those 141 students, how many were girls? 91. So we're going to look at some patterns, and we're going to go back and write these a different way. And the reason we're going to write them a different way is to discover a formula for us. So it says, what do you notice about all the denominators? Well, your denominators, 251, 240, or 227, 241, came from your given information. And what about your numerators? Well, my numerator in the first one was 30. So if I find 30 up here, it's where girls and sports overlap. If I find my numerator of the second, it's 117, which is where boys and grades overlap, and so on. So the numerator is your both. So if I go back up to my first equate, or my first probability statement, there's another way I could actually find this. So since my numerator, again, we discovered was both, I could actually find the probability of sports and girl. And that probability, let's see, sports and girls, so go to your table. So sports and girls is 30 out of 478. That's the population. So that's the probability of selecting out of the population someone who says sports and is a girl. And then my denominator, notice it says your given information. So my given here was a girl. So let's find the probability of a girl. So out of all students, there were 251 girls out of 478. So notice if I were to reduce this fraction, I end up getting 30 over 251, which is the same that I got from the previous statement by just looking at the table. So why did I take time to do that? To show it's the same. Well, if you turn the page, you have actually discovered what is called the given formula, which occasionally you will need when your problems are not as easy as looking at a table. So we're trying to find the probability of B occurring given that A has already occurred. So the probability of B occurring given A has already occurred. We can find that probability by taking the probability of both B and A occurring and dividing that by the probability of A occurring. And so anytime that you're given a given statement, you can use this conditional probability formula to find that. Now the next two examples, you can probably tell me the answer without using this formula. So we're really going to use the formula to justify and to prove that the formula works. So we draw one card and look at it. I tell you it's red. What is the probability that it is a heart? Well, how many red cards are there? There are 26 red cards. Of those red cards, because we already know that to be true, how many of them are hearts? 13. So the probability of this occurring is 1/2. So let's use our formula from up above. So first, notation. What do I know to be true? I know it's a red card, and I'm trying to find the probability of it being a heart. So according to the formula we derived up above, we can find the probability a card is heart and red over the probability the card is red. So remember, we're now talking about out of all 52 cards. So out of all 52 cards, how many are hearts and red? There are 13 red hearts out of 52 cards. In the denominator, we're finding the probability of the card being red. Half the deck is red. So 26 out of 52 cards are red. Notice that reduces to 13 over 26, or 1/2. So our next statement says, what's the probability it is red given that it is a heart? Well, if you think carefully about cards, you know it's a heart. There are 13 hearts. Of those hearts, how many are red? Actually, all of them are. So the probability here is 1. If I wanted to use my notation's the probability of a card being red given that it's a heart. So I find that by doing probability of heart and red over probability of heart. There are 13 red hearts out of all 52 cards. There are 13 hearts out of 52 cards. Hence, we end up with 1. So we're going to switch gears just a little bit and talk about events that are independent and dependent. Remember, we started off that way. And conditional probability of events that come in a sequence, can be independent or dependent. Some examples of independent events would be flipping a coin, drawing a card with replacement. One does not affect the other. Dependent events, one event does impact the other. Drawing a sock and putting it on your foot and then drawing another. You're not replacing that. Picking a card and then picking a second card. So that would be dependent. So let's look at a couple of examples here. 2 cards are selected in sequence from a deck of cards. Find the probability you select a jack and a queen. Okay, so notice this doesn't say given. It just says you're selecting 2 cards. You want to know what's the probability that you select a queen and a jack. Would these be independent or dependent? It would be dependent because the number of cards you have to select from after your first changes. So we're finding the probability that we select a queen and then a jack. Well, the probability of selecting that queen, you have 4 queens out of 52 cards. And multiply, you want to find the probability of selecting a jack. Well, now you only have 51 cards. How many jacks do you have remaining? Well, you still have 4 jacks. And so that ends up giving you 0.0060. This is called the multiplication rule. So let me turn to the next page. The probability that 2 events occur in a sequence is the probability of A and B will equal the probability of A times the probability of B given A. If you think about it, on our previous page, we're taking the probability of a queen and multiplying that by the probability that we draw a jack given the first was a queen. That's why we only have 51 cards remaining. So we used this rule. If the events are independent, we can simplify this equation to the probability of A and B will equal the probability of A times the probability of B. Now, why would we be able to simplify that equation to that? Well, probability of B isn't going to be affected by whatever happened from A. So that would be like tossing a coin twice and it landing on tails. So probability of tails and tails would be 1/2 times 1/2. It makes no difference what your first toss was. Okay, so let's look at some examples here. 2 cards are drawn from a deck of cards without replacement. Find the probability we have an ace and a king. Well, the probability of the first card being an ace would be 4/52. You are not replacing, so therefore, you now have 51 cards to select from. You still have 4 kings. So we get 0.0060. These are dependent events. Number 2, find the probability that both cards are aces. So we're finding the probability that we draw an ace and then draw another ace. Notice it says without replacement. Well, the probability of drawing an ace is 4 out of 52. We're not replacing that card, so we now have 51 cards. Well, how many aces do we have left? We have 3 aces left. Multiply those together, and we get 0.0045. These are dependent events. 2 cards are drawn from a deck of cards. We replace the first card. What's the probability they are both aces? Well, we have 4 aces out of 52 cards. We put that card back. We still have 52 cards, and 4 are aces. 0.0059. These are independent events. The second event was not affected by the next. So 2 events, A and B, are independent if the probability of B given A is the same as the probability of B. In other words, the fact that A occurred does not change the fact that B occurred. This is how you prove if 2 events are independent. Okay, so let's jump on down to our answer. We're trying to prove if these events are independent. If they are independent, the probability of B given A will equal the probability of B. If they are independent. So that's what we need to test. Well, we know the probability of B. That's given up above. I'm going to put a question mark here. We know the probability of B is 0.6. I need to come find the probability of B given A, which we are not explicitly given, but we know how to find that. We find the probability of both occurring and divide it by the probability of A. The probability of both occurring is given to me, 0.2. The probability of A is 0.4. So again, we're looking for does that equal 0.6. So type that in your calculator. Does 0.5 equal 0.6? No. That means we have dependent events. If they were independent, then these 2 probabilities would be the same. The probability of A occurring does not affect the probability of B occurring. So on your next page, you're simply practicing some. So it says, let's practice some probability. We have 10,000 African Americans, and it's determined 27 had sickle cell anemia. So A says, suppose we select one out of the 10,000 surveyed. What's the probability that he or she has sickle cell anemia? Well, we're choosing one person. We have 10,000 people in all. We have 27 people that have sickle cell anemia. So the probability of choosing someone with sickle cell anemia is 0.0027. B part, 2 individuals are selected. What's the probability they both have sickle cell anemia? So we're looking for sickle cell and the second person having sickle cell. We've already found the probability of the first person in the previous step. So we have found someone who has sickle cell anemia. How many people are left out of the 10,000 to choose from for our second person? Well, 9,999. How many people are left that have sickle cell anemia? 26. These are dependent events. We end up getting 0.000007, a very rare occurrence. If two individuals are randomly selected, what's the probability that the first person selected has sickle cell and the second person does not? So again, we have already found the probability that first person has sickle cell. That's 27 over 10,000. We have 9,999 people to pick from. How many of those do not have sickle cell? Well, 27 has sickle cell. How many are left over do not have sickle cell? That would be 9,973. We end up getting 0.0027. You can type that in your calculator. These are still dependent events. The second probability of finding someone who did not have sickle cell was influenced by the first. Okay, so let's look at this table here. So we have a table of juniors and seniors and about what kind of college decisions they have. What is the probability of randomly selecting someone who's undecided? So we have 13 people out of 25 who are undecided. What's the probability of randomly selecting someone who has narrowed it down to at most 2? Well, we know in all we have 25 people. So how many would be at most 2? Well, this is a little tricky. So we know 7 haven't narrowed down to 2. But if you think about it, if you've decided, you only have one choice. And that would be included in the at most 2. So we get 20 over 25. What is the probability of selecting a junior? Once again, we only have 25 students. Of those 25, 8 are juniors. What is the probability of selecting a student who is a junior or is undecided? So the probability of selecting someone who is a junior or undecided. Well, up above, we looked at the probability of a junior. So we have 8 juniors. How many people do we have that's undecided? 5. There's a problem with what we just did. We have 8 juniors. There's the 8 kids we involved in our calculation. We had 5 that were undecided. What do you notice? There's been a group that's been counted twice. We can't count those kids twice. So I'm going to turn around and subtract 4. That way we are only counting them one time. So we end up getting 9 out of 25. Okay, 5. What is the probability of selecting a student who is undecided given they're a junior? Okay, so what do we know to be true about this person? Well, they're a junior. There's only 8 juniors. How many of them are undecided? 4. So we end up getting 1/2. What is the probability of selecting an undecided junior? Do we know anything to be true about this person already? Are we given anything? No. So we're still looking out of all 25 people. So out of those 25, what's the probability of selecting an undecided junior? That would be 4. So 7. Are the events select a student, select a junior, and select a student who's undecided, independent or dependent? If they're independent, the probability of selecting a junior given, a probability of selecting an undecided given they are a junior will equal the probability of an undecided. You could actually prove this another way. You could find the probability of a junior given they're undecided and see if that's the probability, same as the probability of a junior. It really makes no difference. You're just seeing if the probability of being undecided given junior is the same as undecided, The fact that it was a junior didn't influence it, and so therefore it's independent. Again, it makes no difference which way you choose to prove this. I'm going to choose this first method because if you look up above, I've already found the probability of a junior, of undecided given junior. We found that to be 1/2. I also found the probability of being undecided up in number 1. Ooh, which I did number 1 incorrectly. It says undecided, not decided. Hope that didn't mess you up. So let me back up. Probability of undecided. There are 5 students out of the 25. So that would be 1/5. Sorry about that. So let's go back to this last statement. The probability of undecided, which we did find now correctly in number 1, is 1/2. Does 1/2 equal 1/5? No. So therefore, they are dependent. I could go over and do the other one if I wanted to. What's the probability of a junior given they're undecided? So we're only looking out of the 13 undecided people. What's the probability that's a junior would be 1 out of 13. Does that equal the probability of a junior? There are 8 juniors out of 25. Those are not equivalent fractions, and we know it's dependent. That's the end of video 2. You have classwork and homework to complete now.